Alright, today's video is remove k digits. I'm going to show you how we can solve this using something called a Deque, or a double-ended queue. Okay, so here is an example, and let's just do an easy one. Let's just do k equals 1. So this is asking us if we could remove a single digit to make this the smallest possible number, which digit should we remove? Now we might be tempted to remove 9 because 9 is the biggest digit, but that means we would get something like 1, 4, 5, 2, 1. But I can show you another pair where if we remove this 5, we get 1, 4. If we remove this 5, this 2 shifts over, so we get 1, 4, 2, 1, 9. You can see here that 200 is smaller than 500, so this is actually an even better solution. So it's not just enough that we take care of the biggest number, but we also need to take care of the most significant number, reading from left to right. So this is a more significant position than 9. And we also want to get the digit where something smaller can take its place. So let's think about this question again. Okay, so if we read from left to right, we first read 1. And if we were to remove 1, that means that the next digit, which is 4, would be able to take its place. But 4 is a much bigger number than 1, so we don't want that to happen. So we'll keep both of them for now. So now let's compare 4 and 5. If we remove 4, 5 would take its place, which is even bigger, so we also don't want that, so we'll keep them both. Now let's compare 5 and 2. If we were to remove 5, 2 would take its place, which is actually fine, right? So that would give us a smaller number. So we can actually remove this 5. And of course, we can put in our 1 and 9 to get our first solution. Now what happens if we do k equals 2? Well, actually, k equals 2 is just the same thing as k equals 1 plus 1, right? So this is the same thing as 1 plus 1. So we can actually skip forward to where we removed our first digit. So when we removed our first digit, it looks something like this: 1, 4, 5, 2, and we decided to remove this 5. So now we actually take a look at previously, this 4 we kept, but now because of this new 4 to 2 comparison, we would want this 4 to be replaced by 2. So we'd actually remove this 4 instead. And then again, we would have 1, 9 following over here. Okay, so let's take a look at k equals 3. So again, this is just the same thing as 2 plus 1. So let's just fast forward to where we were at the end of removing the second digit, which was 1, 4, 5, 2. This got removed, this got removed. Okay, so now we can see here that we have to double check that the previous one still aligns with the next one. So if we remove 1, it'd be replaced with a bigger number, so we don't want to remove 1. We'll still keep 1. So let's continue on here. We'll read 1, so 1 comes down, and you can see here that we want to replace 2 with a smaller 1, so we're going to remove this. And then we add the 9 to get our 119. So before here was 1219 and 14219. Okay, last example, k equals 4. Again, we'll skip over to 3 plus 1. So we'll skip over to what happened at 3. So at 3, we're in this situation of 1. This got removed, this got removed, this got removed, and we also had a 1 here. So we'll check the previous one as we did before, and you can see here that 1, if we were to remove it, gets replaced by another 1. So really there's no change at all. So we'll keep both of them. And now we'll read this 9. If 1 got replaced by this 9, this would be a lot bigger. So we also want to keep this 1. Now if 9, there's nothing else to compare it with. So we can think of this as just nothing. So if 9 got replaced with something, or with nothing, then that's definitely better than having something, which is 9. So you'd much rather 9 be replaced with nothing. So this is going to get deleted, and this gets us our final solution of 11. So the way that we can think of this is really this is just a stack, right? So we had in the beginning 1. and then we read 4. And then because, this was still increasing, so 1 went up to 4, 4 went up to 5. But then at this point, when we're comparing 5 with 2, 5 went down to 2. So because of that, we wanted to pop off this 5, or in other words, delete it. So that was our stack situation. And then when we wanted to solve k equals 2, we could actually just continue using the same stack. So we were at this state, right? And then this was already popped off. And then we were comparing between this 4 and this 2. And then because 4 is bigger than 2, this also got popped off. And then repeating our k equals 3, we now had 1 here. And then, all of these got removed, so we'll put them away. Well, actually, just these two so far. And then we read this 2. Now, because this 2 is bigger than 1, so it was going upwards, we'll keep it in our stack. And then at this point, 2 read 1, and 1 is smaller, so we learned that actually we do want it to pop this off after all. So we pop this off. And then for the final one, we started off with 1. 1 and 1 are okay, so 1 will get 1. And then we had 9, which was also okay because it was going up. So remember, every time that it goes up, we will keep it into our stack because we don't want the bigger number replacing us. But then 9, compared against empty, definitely wants to be popped off the stack. It wants to be replaced with something smaller, and nothing is smaller than everything, right? So here we get popped off, and then finally we had our answer of 11. So this is how we're going to use a stack to figure out which digits to delete. But we also need the advantage of a queue, because in order to build our number, we need to read from left to right. So a stack allows us to read from right to left. So a stack allows us to go this direction. Here's the stack. But a queue allows us to go from this direction. And in order to build our number, 1, 2, 3, 4, 5, 6, we want to read it as a queue. So instead, the data structure that we'll use is something called a Deque, which stands for a double-ended queue. So this has the advantage of both a queue and a stack at the same time. So let's try coding this out. So we will have our array Deque of characters, because this is a big string, so everything is represented as characters. So array Deque of character Deque equals new array Deque. Now we have to read the characters, so we will have chars equal to num.toCharArray. Now, a hint for the second part, we're actually going to see how we can use this chars array to simulate the array Deque and get rid of the array Deque in our second solution. But for now, let's keep it. And we need to read in our chars array. So let's have some sort of a count index into our chars array. We'll start it at 0. And we'll initialize our chars array. So Deque dot add last. So we're going to add last for it to be a stack. Will be chars at I++. So this I++ just means we'll read it at I, and then we'll increment it by 1 afterwards. So next time we read I, it'll be correct. So that's the same thing as going chars at I, and then I++. Okay, so we have that so far. Nice. And now we want to read every single, we want to remove k amount of digits. So let's do int j equals 0, j less than k, j++. So in each iteration, we're going to remove a digit. So let's think of the two cases where we would remove digits. So the first case is we're comparing against nothing, so we compare against nothing. The second case is, so the first case is top, or the head of the stack, so the top of the stack compare against nothing. And the other case is top compare against something smaller. It's when we would remove a digit. So this will be if, let's see, if we are at I is equal to n, so we'll have int n is equal to num dot length. So that means that there is nothing else to compare. Nothing to compare anymore. So that is this case right here. With the 9, we had nothing to compare it against, so we just deleted it. So if I is equal to n, then we can do deque.remove last. Okay, so top compares smaller. That means if there's actually something in our deque, so it's not empty, and deque.get last is, let's see, what do we want here? We want to see this 5 to 2. So if this top of our deque is bigger than the next character that we're reading. So if deque.getLast is bigger than char is at I, then we also want to remove last. Now if both of these cases don't work, then we want to add it into our deque. So that's the case of 1 reading 4. We don't want 1 to be removed because that means it would get replaced by this massive 4, so we keep 1 and 4 in our deque. So that would be deque add last char is I++. Now there's something wrong here because we're supposed to remove a digit each iteration, but we only remove in this and this. We don't actually remove here. So what we'll do is we'll wrap this in a while true statement. So by wrapping in a while true statement, that means we can break here because we removed a digit, break here because we removed a digit. Otherwise, we'll keep adding on to our stack until one of these two cases happen. So that means by the end here, we have removed k digits. After we removed k digits, we need to fill in the rest of the numbers that we haven't read yet. So you can imagine if we had a number like 911, and then we had k equals 1, we would remove 9 very fast, but we haven't put in these ones into our deque yet. So while deque size is smaller than our final size, so our final size is going to be the original string minus k digits. We will do k.addLast chars I++. So this will fill in, so this is a fill in rest of digits. Okay, so the next step is now to start printing the string. So to print the string, first thing we have to do is we have to remove the leading zeros. So that means while deque is not empty, and deque.getFirst is equal to 0, then what we want to do here is deque.remove first. So remove the leading zeros. And this is where we use deque as a queue instead, by reading the first. Whereas here we're using it as a stack by operating on the last. Okay, so now that we remove leading zeros, we can now build our string. Okay, and now to build our string, we start from the left side. So again, using it as a queue. What we'll have is sb.append deque.remove first. And then at the end here, we can return sb.toString. Now there is an edge case. What if the string is empty? Well, if the string is empty, that's the same thing as saying that it's 0, right? So if we removed all the digits from the number and it's left with nothing, then that's just 0. So that means sb.length is equal to 0, means we'll return 0 instead. Otherwise, we will return sb.toString. And another one that we can add here is at the very beginning, if n is equal to k, so if we removed all the digits, then we can also just return 0 without doing any of this work. Okay, let's see if there are any mistakes. Cool, so at this point we have a working solution. Now if you're interested, for the next part I'm going to go over how we can replace this chars with, how we can use this chars and simulate a deck from it without having an actual deck. Okay, so let's get down to it. Let's see what we want to do here. So you can see here that with this deck, we're really just keeping track of 2 pointers. One for where we're reading next, and one for the head of the stack. So here is the head of the stack, here's the next number we're reading, here's the head of the stack, here's the next number we're reading. So instead of an array deck, all we'll do is we'll keep track of the top. So the top of our stack. So if this was our stack, here is the top. And we can use the same chars array as this. Because we're reading from left to right, and we're deleting digits, it means that we're never going to overwrite something that we haven't already read, and there's enough space to put in our whole answer. So what will that look like? We have our chars. Now we need some sort of a top instead of this deck. We'll initialize it at -1. So there's nothing in our stack yet, so the top is -1. Now to add something to our stack, it's going to look like chars at ++ top is going to be equal to chars at I++. So this means, so let's say we had ABC, for example. In the beginning we had top here, and we had I here. What we'll have at the end of this is we will have I here, and we'll have top here. And top will have overwrote A with A. So I guess a better example is let's put I here for some reason. If we had I here, what we'll have after executing this statement is we'll have this become D and this go to E. So that's what this line does. Okay. So remove last is as simple as just saying top minus minus. And then here, what we're doing is basically a bound checking, making sure that there's actually something in top. So all we'll have to do here is replace this with top greater than or equal to 0. And here, get last is really just chars at top. Remove last is top minus minus. Add last is chars at ++ top equal chars at I++. Okay, so what we'll have here is the size of the deck is really just the top of the stack plus 1. So the last index plus 1 gives you the size. And then again, we'll do chars at ++ top is equal to chars at I++. Okay, so now we want to remove leading zeros. This part's a little bit different. What we want to do is, let's say our number is something like this. We have our top here, and we want to somehow move the start of our array. We want to mark that the start of our array starts here. So what we'll do is we'll keep track of I equals 0, and then while I is less than top plus 1, so while it's still within our simulated deck, and chars at I is equal to 0, we'll do I++. So that means at the end of this while loop, we'll shift I from its original position of in the beginning all the way up to I here. And then that means at the very end, when we build our string, we can now actually use this version. New string, our chars, the offset, and the length. So we can, instead of all of this, we can return new string with this chars, the offset means we start at I instead, and the length is going to be top plus 1 minus our offset of I. Oh, but we need this edge case of what if there's nothing. So what if there's nothing will look like if I is greater than top. So if I is greater than top, then return 0. Otherwise, it's new string. Right? So if I was here, then that doesn't make sense. That means that there is no string. So we can do that instead. And this should still work if I typed everything correctly. Cool. Okay, so I forgot to go over the runtime, so let's do that real quick. The runtime here, we have O of k, definitely. But then we have this while loop embedded inside. Now we might think that this might make it O of k times n because we're looping over our characters in here. But notice that we are always doing I++ in here, and this I is outside of our for loop, which means this while loop will only increment at most I times. So this is, or n times. So this is actually O of k plus n. And this space, well, because we have to return a string, is also O of n. Okay, that's the end of today. It's a little bit more complex today, so if you have questions, just let me know in the comments. And I'll see you on the next one.